Hello everyone and welcome to another video. Today I'd like to talk about the final value theorem. And we will see that the final value theorem is a neat little theorem and tool that's going to allow us to relate how a signal at steady state in the time domain behaves and is related to how that same signal relates and behaves in the Laplace or the S domain here. So let's just write down the gist of what this thing does here. So again, let's say you've got a signal here in the time domain. Let's call it f of t here. And if its limit as time goes to infinity exists, then the final value theorem, I'm going to call it FVT so I don't have to keep rewriting this thing all over here. So what the final value theorem does is it allows us to relate the steady state behavior of f of t, in other words, this quantity here, to the behavior of the quantity s times the Laplace transform of the signal here, s f of s, okay? So in other words, we see it allows us to relate the steady state relationship, or where the signal goes in the time domain at steady state, to how this term in the Laplace domain behaves, okay? So maybe what we should do is let's state the proof, or state the theorem, and then we'll go ahead and prove how it is derived, as well as talk a little bit about it and go through an example here. So again, here's the theorem here. Maybe let's do it over on this side here. So the theorem is that if f of t and its partial, or sorry, its derivative df of t dt are Laplace transformable, so this is all that good stuff, like these signals are of exponential order and basically their Laplace transform exists. So first of all, their Laplace transforms have to exist, and if the limit as time goes to infinity of f of t exists, in other words, if it does actually go to some steady state value here, then this steady state value, right, which we said is limit as t goes to infinity of f of t, this is just going to be equal to the limit as s goes to 0 of the quantity s times f sub s. Okay, so this is what we want to look at. This is basically the final value theorem here. And again, we see that it's useful that if all I care about is the steady state behavior of the signal here, I can just use the Laplace version of that signal, multiply it by s, and then take the limit as s goes to 0. Okay, so let's do a quick proof of this just so we can see where this comes from. Okay, so let's examine the differentiation theorem. Basically, it's the Laplace transform of a derivative here. So if you remember in our previous video, this one over here, right, we talked about the Laplace transform of different functions here, and the one that I mentioned would probably be the most helpful when working with differential equations or dynamic systems is the differentiation theorem, where we related how the derivative of a signal is related to the Laplace domain, and we saw that basically derivatives in the time domain show up as s's in the Laplace domain here. So let's just recall that here. So let's just say recall the differentiation theorem. Right? And basically, let's just take one derivative here. So in the previous video, we talked about how this could be extended to the nth order derivative here. But basically, we're saying that if I have the first derivative of the function and I take its Laplace transform, right? Didn't we basically show that this is the same thing as f of s, right? So again, this derivative in the time domain shows up as an s in the Laplace domain here, but then we need to take into account the initial condition. So I'll make lowercase f of 0, okay? All right, so let's go ahead and let's use the definition of the Laplace transform on the left-hand side. So again, if you recall, right, the definition of the Laplace transform, or this Laplace operator, I'm writing it like such, right? Basically what it said here is that if you are taking the Laplace transform of any function here, right, what do? Well, you take the function itself, right? In this case, it's f prime. You multiply it by e to the negative st, right? And then you integrate from 0 to infinity dt. right? So that's just rewriting the left-hand side. This is just the definition of the Laplace transform of f prime of t. Here it is, right? Okay, and then I leave the right-hand side unchanged, right? So this is now just still s f sub s minus f of 0. Okay? Okay, now let's take the limit of both sides as s goes to 0. So take limit as s goes to 0 on both sides. Okay, so we see here, if you do this, the limit as s goes to 0 of this entire integral here, well, you notice here, e to the minus st, right? The limit as that goes to 0, maybe we should write this down here. So let's just make a note here. Note here that limit as s goes to 0 of e to the negative st, right? Isn't that just 1, right? Because this s is going to go to 0, right? So this left-hand side can be simplified down to integral 0 to infinity here of f prime of t times 1, right? I guess I don't even need to write that, dt, right, is equal to the right-hand side still unchanged, right? F of s minus f0, right? Okay, so now if you look at this side here, the left-hand side, this is basically the fundamental theorem of calculus, right? This is like I'm taking the integral of the derivative of a function here, so it's really just the function evaluated at the two endpoints of this integral here, right? So this left-hand side here is just simply f at infinity, right, minus f at 0, right, is equal to s f sub s minus f0, right? Okay, great. So now if you look at this, these initial conditions cancel out. So here's f0 here, here's f0 over here. So, oh, sorry. I got too excited here. Sorry, I was taking the limit of s goes on both sides. So sorry, this side should have been limit as s goes to 0 of the whole quantity s f sub s minus f0, right? And sorry, before we do the cancellation, sorry, maybe I got too excited here where we were going. Let's do this left side. Because there's no s in here, right? This is the initial condition in the time domain, so the limit doesn't affect it, right? So I can move this to the other side. So now I have limit as s goes to 0 of the quantity s f sub s, right? That's the end of the limit, right? Minus f0, right? This f can come out of the limit. And now I can cancel both sides here, right? And we end up now with the result that we're looking for here, that f infinity is equal to the limit as s goes to 0 of the quantity s times f sub s, right? So here we go. Box that guy up. That's basically our proof here, because what it basically says here is the function at time equals infinity, aka the steady state behavior of the system, is equal to this, right? It's the limit as s goes to 0 of the quantity s times f sub s, right? Okay, we got to make one little note here before we keep going here. Before we start applying this, I want to make one note here, and actually it's related to, oh crud, exactly the term I just erased here, right? We said that this whole thing only works if the limit of the signal in the time domain as it goes to infinity, if that is equal, is actually exists, right? Okay, so let's just make a quick note here. So the aforementioned proof only applies if the limit as t goes to infinity of f of t exists, right? This is another way of basically saying only if this thing does go to a steady state value here, right? Otherwise, it doesn't make any sense at all here. And we're going to see a couple examples of that here in a second here, okay? So what we see that we actually need to have happen in order for this to be true, another way to put this, and another way that's actually going to be a little bit more useful here, is we're going to see that we can just write that this requires that basically the quantity s times f sub s has all poles strictly in the left half plane, basically of your real imaginary axis, right? So the other way you could think about that here is that this quantity, it's the quantity of s times f sub s. It's not just the function of the Laplace domain itself. You have to multiply it by s. That quantity has to have strictly negative real parts of all of the poles, right? So when I go ahead and plot the poles in the real imaginary axis of this quantity s times f sub s, they better all lie out here, and they cannot actually be on the line here. This is not allowed, and I guess x is a bad thing to use because I wanted to say not allowed, right? Anything here or over is bad, and we have to be, maybe I'll try to draw it like this. So this squiggle means it doesn't include the vertical axis here, so this is okay. Right? If you have poles out there of that quantity, we should be good to go, okay? Okay, so tell you what, that sounds pretty reasonable. Tell you what, why don't you give me a second, I'll pause the video, erase the board, and let's go do an example of this to maybe hit home how this applies and provide some actual physical intuition here on some of these signals. Okay, so let's look at an example of a dynamic system and its response here, and we're going to use our good old friend here, the mass spring damper system. Right, and you guys have seen this many times here, so I probably don't need to spend a lot of time explaining it here, but you basically have a mass with mass m attached to a wall with a spring constant k, with a linear viscous damper with damping coefficient b here, okay? And what I want to do is I want to measure the position here, x of t, of the block here, and I'm also going to be applying some kind of input force u of t here. Okay, so that's a physical setup. You guys have seen this all before, and we showed here that I'm going to just write it down because, again, since you guys have seen this probably so many times here, that the ODE that governs this system for the equations of motion, maybe let's call it / equations of motion here, right? You could write this thing like this: x double dot of t plus b over m x dot of t plus k over m x of t is equal to 1 over m times u of t. Right? Okay, so here it is. Now what I'd like to do here is I would like to understand, where does this block come to rest if I use different kind of inputs here, u of t, to this system here. So let's examine two cases here. So let's go like a case 1 here. Let's apply a step. And then case 2, what we'll investigate in just a second here, is let's apply a ramp. Okay, so let's first take a look at case 1 here, okay? So what I want to do here in case 1 here is I want to look at what is the steady state value in response to what? A step. So a step in this case means, let's just use a magnitude. How about 1 here? So it's just, basically it's like this. It's just a 1. Sometimes it's written as just, 1 of t. That's sometimes how some textbooks write a step here. Or let's just call it 1, right? At time 0, the input force goes to 1 Newton here, or 1 unit of force, whatever you happen to be using to model this problem here, right? Okay, so if this is the case, let's rewrite our equations of motions in response to this input here. So in this case, our equation of motion becomes, it's basically that exact same thing here, right? Except the u just becomes a single 1 here, right? So we get, again, maybe let's just write it down so I'm not skipping any steps. X double dot of t plus 1 b over m times x dot of t plus k over m times x of t is equal to 1 over m times a step input here, right? Okay, so now let's Laplace transform both sides. Laplace transform both sides. Right, so again, this first term, you're going to get an s squared x of s, right, minus our initial conditions here, right, minus s times initial position of the block minus the initial velocity of the block here. So that's the first term. Maybe I'll put this in brackets, right, plus b over m times s, capital X of s, right, minus initial position of the block, plus k over m times x of s, right, is equal to 1 over m. Okay, and now what is the Laplace transform of step input, right? If you remember, that's 1 over s, right? Okay, great. So now what you can do here is you can do a little bit of algebraic manipulation and solve for x of s here, right? So I'm not going to do this here. Feel free to run the Mathematica here or prove to yourself that you could do this boring algebraic manipulation, and you could basically get this thing to say x of s is equal to, what this is going to look like, it's not pretty here, but you can get it to be something like 1 over ms plus s initial position of the block plus initial velocity of the block here plus b over m initial position of the block all over s squared plus b over m s plus k over m. All right? Okay, so maybe let's take a minute to just stop and think, what is this, right? If you think about this long enough, this is the response of system to a step input. But this is in the Laplace domain, right? Right? So it's a little bit hard to plot this and understand what does the block look like, or what is it doing here. But actually, if all we care about is just the steady state value, if I don't care about the transient behavior or what it does to get to steady state, I just want to know where does it go, I can apply final value theorem right here. I don't need to do the whole partial fraction expansion and then inverse Laplace transform and all that kind of gobbledygook here to get this back in the time domain, because I can just look at the signal in the Laplace domain and try to figure out, and use it to figure out where does the block go in the time domain at steady state. Okay, so before we do that though, let's do that one thing that we talked about earlier that I said was kind of this potential spot for getting tripped up here, is we need to check to make sure that the poles of the quantity s times x of s are in the left half plane. We want to make sure that this block eventually does go to some steady state position. I mean, you know it should just from physical intuition, right? You know that if you have a mass spring damper system and you put 1 Newton of force on it, it might oscillate, it might do some crazy stuff, but eventually it will come to rest here. Let's make sure that that's the case though from a mathematical perspective, right? So what we need to do here is first, let's go ahead and check that s times x of s has poles in left half plane, right? And again, make sure you note I need to check that s times x of s. I can't tell you the number of students that just check x of s. It's the quantity s times x of s that you need to do, okay? So if you do that, again, run over to Mathematica here and just take this gobbledygook down here, this thing right here, just multiply it by s, and again, let me see, you can simplify this thing, you could write it down. I don't want to jump over to Mathematica because I think it's going to break our stride here, but here's what I got in Mathematica when I did this. This is 1 plus bs times x0 plus ms times the quantity s x0 plus x dot 0. That was the numerator. And then the denominator was, k plus s times the quantity b plus ms. Okay? Again, all it was is this thing, and you hit this, multiply it by an s, and you simplify it, and you can get it down to this, okay? So again, let's just go to Mathematica, have it solve for the roots of the characteristic equation, or the poles here, and we'll see what we end up with here. So again, I don't want to jump over to Mathematica here, but let's just assume that we do here. So solve for poles, right? Okay, so basically what you would end up for here is solutions to this second order polynomial, right? There's 2 poles. You end up with pole 1 here is located at, what do we end up with here? Yeah, so we have S1 here. Here's one of the poles here. This is at minus b. Actually, I guess it's minus the quantity b plus square root of b squared minus km all over 2m. And the second pole is basically, it's kind of its complex conjugate as you would expect here, right? Negative b plus square root of b squared minus 4km all over 2m. Okay? So let's go ahead and erase some of this here. Okay. Okay, so now what we need to do here is, can we show that those 2 poles are always negative here, right? So let's look at the first pole. So examine pole 1. Okay, so what we see here is we need this thing minus b plus square root of b squared minus km all over 2m to be strictly less than 0 here, right? Or at least, I guess technically we need its real part to be strictly less than 0, but I think you get what I'm saying here. Okay, so here we can start making some assumptions. So let's go ahead and assume that the mass of this block is strictly positive, which makes sense here, right? You got a mass here. I've never heard of a 0 mass system, or even less a negative mass system. So this seems totally reasonable. If that's true, I can just multiply by 2m and I don't have to change the sign of this thing, right? So in this case, we end up now with negative b plus square root of b squared minus km. It's got to be less than 0. Okay, let's get this negative. Well, let me see. Maybe the other way to think about this here. Yeah, I guess we can just actually probably look at this directly right now. So if you look at this here, let's go again and again assume that k and m are both positive, right? So again, that makes perfectly good sense. So k is strictly positive, and we already assumed that m is strictly positive. So again, the spring constant, it has to be a spring which provides restoring force to the system here, right? If that's the case here, this entire term, this square root term, right, it has to be less than b, right? Or imaginary, right? So if this is true, right, we see that this term here, square root of b squared minus km, right? This has to be less than 0 or imaginary. In any regard, its real parts, its magnitude's got to be less than b here, right? Because all this term is going to be, it's going to be some positive value, which is going to take away from this b squared term. So by the time you take the square root, this thing's got to be less than b. So great. By the time you do this here, yeah, this thing, yeah, there's no way that this entire thing becomes positive here, right? So we say check. This works out, right? This pole 1 is always going to be negative as long as the damping ratio, or sorry, the mass, the spring constant, and I guess, you know what, I guess we did have to make the assumption that b is also going to be positive here, right? So we also have to assume that b is going to be positive, which again makes sense. You're in a fluid, or that damper takes energy out of the system rather than adding energy here, right? If all of these are true, if mass, k, and b are all strictly positive, this pole is all fine, right? It's all strictly in the left half plane. We can do the exact same analysis for the second pole here, right? So let's do pole 2 here. So the analysis is going to be surprisingly similar, right? I think there's only a sign, S-I-G-N change. So now it's just that, right? That's the only thing we're checking. Here's pole 2. I got to still make sure this is 0. Again, let's assume mass is greater than 0 here, so this thing goes away. So I now have minus b plus square root of b squared minus km, right? It's got to be strictly less than 0. And again, we make the same assumption, right? So let's assume that k and b are strictly positive here. And again, we make the exact same argument. This is still the same square root, so that all applies. This whole square root has got to be less than b here. So if it's less than b and you add it to negative b here, right, there's no, again, this gets closer to 0, but this one is still never positive here, right? This entire quantity has got to be still strictly in the left half plane here, right? So again, check, this works. So in all cases where you have a positive mass, a positive damping ratio, and a positive spring constant, both of these poles are in the left half plane. So great, this thing should come to rest at some point, and we can apply final value theorem, right? Okay, so now that we did the check, let's go ahead and apply final value theorem, okay? So apply final value theorem, okay? So again, what we're doing right here is we want to look at the limit as time goes to infinity, right, of the block's position here, right? I want to know where the block ends up. And final value theorem says that, okay, that's the same thing as limit as s goes to 0 of s times x of s. And we can now apply this because we just did the check and we saw that it worked. So what I need to do here is take the limit as this quantity goes to 0. That's what we just wrote over here, right? So all I need to do is just start axing out all the s's here, right? So this whole thing is gone. This is gone, which actually knocks out this entire term here, right? And then down here in the denominator, this is gone. This s takes out that entire denominator. And look at this. What do you end up with here? So what we end up with here is this is just equal to 1 over k. Okay? So this is basically x steady state. I guess I don't want to say of t here because it doesn't change with time here, right? So here you go. Now, let's always, what I always like to do is you get some result, I like to apply what I call the engineering duh check, right? We need to make sure, does this make any physical sense? Remember what our system it was, right? You got this block here, hooked up to the wall through a spring here, and you got this damper, B, and we're pulling on this thing with force, in this case, 1 Newton, right? And I'm measuring the position. And what I just claimed here, what the final value theorem told me, is that this thing is going to come to rest over here, where this distance here is 1 over k. right? This is my steady state deflection here, right? Here's x steady state. And again, this should hopefully make sense because again, the initial conditions did not show up here, right? So you notice here, it comes to rest at the same location irregardless of where the initial position or where the initial velocity of the block was. Also, who cares what kind of damper you've got on this? In this case, it doesn't. B doesn't show up anywhere in your solution. And this makes perfectly good sense if you think about it long enough, because what are we doing to the system? We are applying a constant 1 Newton on it, right? The way this thing is going to come to rest or come to equilibrium is if the spring, F by the spring, has to provide a equilibrium, right, of exactly 1 Newton in the opposite direction here, right? Well, the way the spring is going to apply 1 Newton in the opposite direction here is if you deflect it by 1 over the spring constant. So by the time you multiply the deflection times the spring constant, you get 1 Newton here. So again, this all checks out, and this seems great, right? And again, let's just take one step back and think about where we are here and why this is helpful. This is helpful because we didn't do any inverse Laplace transforms or partial fraction expansions or anything at all, right? We worked with the signal directly in the Laplace domain or in the S domain to figure out and predict where the system was going to go in the time domain at steady state, right? So keep in mind here, right? There's no discussion on transient or anything like that here. Okay, so great. So this looked pretty reasonable. Let's do the same thing now for that case 2 we were talking about. So case 2 here is that, I guess we got to erase some of this, right? Okay, so case 2 was going to be a ramp input, right? So in this case, the input force is not a constant 1 here, but let's just make it a linear time t here, right? So the force that is applied to the block just starts at 0, but it just increases like this, right, at a linear rate. So we just start pulling on it or pushing on it harder and harder and harder, right? Okay, so now what we need to do here is, again, let's go through our step here to see if we can find out where the final value or where the resting place of this block is going to be here, right? So what we need to do here is compute the quantity s times x of s, right? And before, actually, tell you what, let's back up one here step. We should have actually, we got to compute x of s first, right? Right? So I got to get that. So again, we go back to our original differential equation, right? X double dot of t plus b over m x dot of t plus k over m x of t is equal to 1 over m times, the input is now time t here, right? So now I Laplace transform everything. The left-hand side, this is the same as last time, right? You take the Laplace transforms, you get an s squared, you get an s, all this stuff shows up. It's the same thing. Over here, though, this is now different, right? The Laplace transform of a single ramp, right? This is 1 over s squared now, right? Okay, so again, you do all this stuff. Now you solve for x of s, right? Okay. And what you're going to end up with here is, again, I'm going to save everyone the boring algebraic manipulations here, but if you solve for x of s, you get 1 over the quantity ms squared times s squared plus b over ms plus k over m. Okay? Great. Okay, so now what I need to do, this here is the signal or the response to a... And actually, where did I? Oh, sorry. You know what I did here? I made the assumption here because we saw that initial conditions really don't matter here. But solve for x of s, and we're going to assume x0 and x dot 0 are 0. So basically, the block starts at rest here. Then we start applying this ramp. All this analysis would go through even if we had non-zero initial conditions, but I don't want to have to write all of that garbage up here, okay? So here's what we end up with. This is the response to a ramp with 0 initial conditions here, right? But again, it's in the Laplace domain. Okay, so in order to apply final value theorem, right, we need to compute the quantity s times x of s, right? So you see, this is actually pretty easy. All we do is take off one of these s's in the denominator, so we end up with 1 over, ms s times s squared plus b over m s plus k over m. Okay? Okay, so now we need to check to make sure that we are safe to apply final value theorem. Okay, so what we need to do here is check the poles of that system here. So again, we solve the denominator is equal to 0, and you can kind of see right off the bat, there's a pole right here. So here are the poles. S1 is just at s equals 0, and then S2 and S3, these are actually the same things that we had earlier here, right? And we showed that these two are always strictly in the left half plane. But this one is the kind of the problem child here, right? This is definitely not strictly in the left half plane. It is sitting right there on the imaginary axis. So in this case, problem, you cannot apply final value theorem, right? And again, if we go and look at the physical block here, the setup, you can see why this doesn't work. Okay? Because in this system, what are we doing? We are increasing the force linearly, right? It just gets more and more and more and more force. So what's going to end up happening is actually this block is never going to come to rest at a steady state value, right? Because it's always going to be creeping to the right as you continually apply more and more force. So there is no final value. So in other words, the limit as time goes to infinity of x of t doesn't exist, right? I mean, I guess you could say it's infinity here, but it basically just keeps going here, okay? So you see that in response to a ramp, we can't predict the final value of the system here, right? Now, I think this is a good spot to stop our discussion on final value theorem here, but note here, maybe this is a good teaser here for some of our future discussions where we will investigate the behavior of the system here in response to a ramp here. So you can totally still analyze systems here and look at what their steady state behavior is. For example, if you apply a ramp, there's probably some good idea that this block is going to probably approach some other kind of ramp, right? It's going to keep creeping to the right as you keep pushing it more and more and more. But in order to get that, it doesn't come to a final value, right? I can't say it rests at 63.8 meters to the right, right? It's going to continually keep moving. But its behavior might settle into some sort of steady state behavior. So again, this is my long-winded trailer or teaser to some of the time domain analysis discussions that we're going to have in the future, okay? So that being said, I think this is a good spot to leave final value theorem. We're going to use this here when we discuss things like DC gain and, like I said, for when we look at time domain analysis of first and second order systems here. So I hope I'll catch you on one of those videos. If you enjoyed the discussion today, please go ahead and like and subscribe to this channel here. It really helps me continue making these. And I hope to catch you at one of these future lectures. Until then, talk to you later. Bye.